Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 5 on earth pressure theories. In the previous lecture, we have learnt about Coulomb's theory of earth pressure, and then we discussed about merits of Coulomb's theory over Rankine's theory, and then we also discussed about Kalman's graphical method for computation of earth pressure. In this lecture, we look into the how we can estimate passive thrust based on Kalman's method, and applications of earth pressures. One of the important and prominent application is in the design of bulkheads. The bulkheads basically two types: cantilever sheet pile walls and anchored sheet pile walls. So in this lecture we try to cover or look into these aspects. So as discussed in the previous lecture, we discussed that Kalman's method is it can be used for determining active or passive earth pressure thrust, and basically this is a graphical method. So what we need to do is that first we need to represent the wall to a scale and the ground surface, and any surface like in this slide which is shown here, where you have got range of surfaces like AC1 and C1 to C2 with another slope C2 to C3 and C3 to C4 and C4 to C5. And in case if there is a some railway track or a boundary wall which is running very close to the retaining wall, then effect of this external load on the earth pressure can also be determined very easily by using Kalman's method. So this slide shows a method for considering external line load on the backfill surface. So what we need to do is that we need to represent this particular wall to a scale, and we need to draw a slope line with an angle phi. Then you need to draw earth pressure line with an angle psi is equal to alpha minus delta from the slope line. Once we draw, then along the ground surface to A, C1, C2, C3, C4 and C5, we need to draw the lines passing from the heel of the wall to the ground surface. So these are nothing but wedge lines. Possibly one of these lines can become a potential failure surface. So here when you look, we have drawn lines like BC1, BC2, BC3, BC4, BC5 passing through the heel of the wall. B is the point here. Then once we have done, we have found out the weight of this wedge ABC1, then represent the weight of this wedge along the slope line to a suitable scale here. Similarly, determine the weight of the wedge ABC2 and determine its scale and then put it on the slope line. Once we do, we will be able to represent this wedge weights along the slope line, and in case if there is a external load coming, add this load at this point here to this particular point of wedge. So then what will happen is that this is that envelope which we are going to get after considering the external load, and this is the envelope, Kalman's envelope, without considering the external load. So once after plotting, we need to draw a line parallel to the earth pressure line, and it should cut at that point where BC1 is there, and that is the point P1 on the envelope. Similarly, P2 on the envelope, P3 on the P3, P4, P5 can be identified, and line joining this P1, P2, P3, P4, P5 will give the Kalman's envelope. In this figure, what we saw is a Kalman's envelope which is drawn for without any load, and this is P1, P2, P2 dash, and then these corresponding points, they represent the Kalman's envelope with the line load. Okay, so this is how we need to consider the external loads coming on to the picture. Now let us look into how we can consider this Kalman's method for the passive case. So we look into the animation here. This is a case for passive case and with a positive wall friction. So this is indicated, and wall face is vertical, having a wall face interface friction is about delta. Then the weight line or slope line is drawn at phi below horizontal. Then earth pressure line is drawn at an angle from the slope line, which is psi is equal to alpha plus delta. Then we now try to draw the trail wedges. So we have drawn the first wedge line passing through the heel of the wall. So this procedure is again same. Here in this case, the wall is actually moving towards the fill. Now what we need to do is that we have to compute the weight of that wedge, and we to represent that weight along this slope line. So that's what we did, and we have drawn a line parallel to the earth pressure line. So this is the point where it cuts. So this is one of the points on the possible Kalman's envelope for passive case. Now similarly along the second line, when it goes and it meets at this particular point. Similarly third wedge line, fourth wedge line, fifth wedge line. When we look into this, all these points can be joined, and then this envelope, this pink one which represents is the Kalman's envelope, and line drawing parallel to this slope line will actually give the one which is passing through this, that is this particular one will give the minimum force, that is which exerted on the wall, that is PP, can be termed here as passive earth pressure thrust. Similarly, Kalman's method for the passive case can also be determined. In this case, a wall cross section is shown, and wall above, when the ground surface above this point, when the wall tries to move this direction, so this portion becomes the active side and this portion becomes the passive side, and when the wall is moving towards this portion will be subjected to compression. So in this case, we are interested in determining the passive thrust exerted by the fill opposite to the wall when the wall is moving towards it. So in this case, a wall cross section is shown, and which is represented here, and a positive wall friction is considered here, and PP is the one which we need to determine. So this is the heel of the wall. So what we have done from this point, heel point, and with the horizontal at an angle psi, we have drawn a slope line, and from this slope line we have drawn an earth pressure line which is at psi is equal to alpha plus delta. Then what we did is that we have drawn number of lines passing to the heel 1, 2, 3, 4, 5, 6. These are the possible wedge surfaces, because we do not know which one will give the minimum earth pressure thrust on the wall. So we need to find out that what we do is that we have taken this, and then we have found out the weight of this wedge, and the weight of this wedge is represented with a suitable scale along the slope line. Then we have drawn a line parallel to that pressure line, and then we have noted a point where it cuts. Similarly repeat this exercise for the other points also. Then what we get is that we generate Kalman's envelope. Once we draw a line parallel to this surface, we can get this point where the earth pressure is minimum, that is PP. That is actually the passive earth pressure thrust offered by the wall when the wall is actually moving towards it. This is only for the portion of soil below in this zone. Now this is the possible, we can say that this is the possible wedge which is actually inducing this force PP. Now PP is the force, passive earth pressure thrust, which is actually determined. Once we know this PP, then we convert into suitable scale, we will be able to get in kilonewton per meter. So by adopting this procedure, we can determine this by using Kalman's method, either active earth pressure thrust or passive earth pressure thrust. Now let us look into the some features of Coulomb's active and passive pressure coefficients. In this case, for different wall friction angles and friction angles of the soil, we have actually given here Coulomb's active pressure coefficients and Coulomb's passive pressure coefficients. When a special case like we discussed with delta is equal to 0 and friction angle is equal to 33, here the Coulomb's active coefficient will be equivalent to the Rankine active coefficient. So the Coulomb's solution can be converged into Rankine solution if those Rankine's wall conditions are satisfied. So let us look into this the deliberations based on this exercise. For the Coulomb case shown in the previous slide with no soil wall friction, that is delta is equal to 0, and a horizontal backfill surface, both Coulomb and Rankine methods yield equal results. That is what we said, that Ka is equal to KAC is equal to Ka Rankine is equal to 1 by 3, KPC is equal to Kp is equal to 3. As the soil becomes stronger, that means denser, and the friction angle increases. So the active pressure coefficient decreases, resulting in a decrease in the active force, and the passive pressure coefficient increases, resulting in an increase in the passive force. So this is we need to note. As the soil increases in strength, that is friction value increases, there is a less horizontal pressure on the wall in the active case. So this indicates that you need to compact the soil so that it induces less pressures on the, in case of active pressure it will be exerting a less pressure. So these are the, this is after NAVFAC design manual 7, where it shows effect of wall movement on the wall and on wall pressure. This is the wall rotation and this is the coefficient of horizontal earth pressure Ka Kp. You can see this is how it varies for loose sand, and for this is a zone for active case and this is a zone for passive case, and this is how this for dense sand. This we already discussed, only this is shown for reference in the diagram form. And also some required displacements like for in sand and clay surface, and in case here active case and wall movement parallel to the wall, then the displacement is required is 0.001 times h, where h is the height of the wall. In case the passive parallel to the wall, then 0.05 times the h, the displacement is required. Similarly, in case of clay parallel to the wall, 0.004 times h, and rotation about the base, then it also requires the similar amount of displacement. General range of wall friction angles, because we have a range of fill materials which can be used. The content which is regarding the type of fill material, how it can be selected, is beyond the scope of these lectures, but we need to have a freely draining backfill so that the pore water pressure is under control all the time. So here the typical fill materials like gravel can have a range of delta, that is interface friction angle is about 27 to 30 degrees. In case of coarse sand, it is around 20 to 28, fine sand 15 to 25, stiff clay 15 to 20, and silty clay is about 12 to 16 degrees interface friction angle. So these are the, this table presents here the general range of wall friction angles for masonry or concrete walls. Now let us look into the application of whatever we have learnt. And first we said that these earth pressures can be used for determining the earth pressures exerted by the soil on the wall in active condition and passive condition, and ultimately these earth pressures can be used for designing these retaining structures. We discussed that many types of retaining structures are there. In the first lecture of the under earth pressure theories, we have introduced the different types of walls which can be possible and which can be constructed, but commonly the walls which are going to be designed like gravity walls and gravity masonry retaining walls or reinforced concrete retaining walls, all these things which require a computation of earth pressure, and based on that the moments are estimated, and then wall stability from the sliding and war turning and from the eccentricity point of view can be considered and can be designed. But let us look into how these bulkheads, what are these bulkheads, how these bulkheads can be analyzed for arriving at their design, or whether they are stable or not, how they will deflect in case if they are anchored with anchor or without anchor. So bulkheads are the most important type of retaining structures after retaining walls, and these are basically used in waterfront applications, basically which are used, these are used in waterfront applications. And bulkheads are sheet pile walls which are made up of number of thin vertical elements called sheet pile walls. So the standard sheet pile sections are available, and these are driven into the ground and connected such a way that it forms a continuous wall. So the wall is very thin, and it has got range of section modulus which is possible. So a typical wall or a typical section can be selected based on the section modulus which is required for a cause. And also there are walls like diaphragm walls which can be constructed by digging a trench and placing a reinforcement and introducing concrete. So bulkheads are sheet pile walls which are made up of a number of thin vertical elements called sheet pile walls, driven in such a way as to form a continuous or reasonably tight wall. And sheet pile walls are widely used for both small and large waterfront structures. So these are also used for, in some cases, like as a part of the berthing structures in the marine environment also. So in this slide, a typical sheet pile wall is shown where these are marked for driving into the soil. Sometimes these are also used for protecting temporary excavations, like in the here what you are seeing here, a high rise building. So to protect any danger or to prevent any collapse of the soil in front of these particularly these sheet pile walls which are driven into the ground to retain the soil behind the this particular section. This is installed sheet pile wall. You can see a case where how the sheet pile wall are installed here with to serve as also as a wall for the retaining this portion of the soil, as well as also to maintain water tightness because of the rubber interlocks, as well as to have a continuous retaining wall. So these are also being in flexible in nature, they are also called flexible retaining structures. So from here onwards we are trying to look into different types of flexible retaining structures and how these flexible retaining structures can be analyzed, what are the salient aspects in the design that we look into it. So basically there are two types, one is cantilever sheet pile wall and other one is called anchored sheet pile wall or anchored bulkhead. Cantilever sheet pile wall is nothing but which is having a section which is shown here driven into the ground, and H is the retaining height and D is the embedded depth, and this line is called dredge level. So the stability of the wall depends upon the embedded depth which is provided in front of the wall. So it derives its stability based on its embedded depth which is there in front of it. So particularly in case where there is a water environment is there, it is required to be checked from the scour point of view, otherwise they can endanger the stability of a structure. Sometimes the wall heights are more than 5 meters. These are actually used up to 5 meters, 5 to 6 meters. But in case for height of the retaining height is say more than 6 meters, then to manage with the given section, they are anchored by using an anchor plate or a anchor sheet pile wall, or by using number of or with the baited piles, they are actually anchored along the length of the wall. And this particular portion which is called tie rod. So these tie rods, they even have with high tensile rods which have up to 100 mm diameter also are being used in the practice. So here also the H is the one which is the retaining height and D is the embedded depth. So the design involves finding out at pressures and estimating D and estimating the anchor forces, so that the design sections can be like the what section to be provided for this case and what is the diameter of the tie rod to be provided and what will be the one safe location of this this anchor plate or a dead man anchor has to be seen. So this actually has to derive its support, it's because of the net resistance, earth pressure resistance. When this is moving this side, here it is possible that there is a active case and here it is possibly that there is a passive case. So that net pressure actually serves as a anchorage capacity for this case. So we introduced in this slide like two types of flexible retaining structures. One is cantilever sheet pile walls and anchored sheet pile walls. Let us look into some features of these cantilever bulkheads or cantilever sheet pile walls or anchor sheet pile walls or anchored bulkheads. In the cantilever bulkheads, basically as we discuss, they derive their support from ground penetration, that is the depth which is embedded. And effective embedment length must be sufficient to prevent overturning. So that embedded depth should be sufficient to prevent any overturning. If it is inadequate, it's possible that the overturning can occur. And toe cover results in a loss of embedment depth and threatens to the stability of such structures. So if there is any cover in front of the wall and that causes a loss of the embedment depth and causes threatens to the stability of such structures. And anchored bulkheads basically gain additional support from anchors embedded on the landward side or from the structural piles placed at a batter on the seaward side. These cantilever sheet pile walls also can be propped externally. They are also called propped walls or propped cantilever walls. Or if you are using anchors within the land side or a soil side, then they have to be these tie rods can be connected and placed at a suitable location so that they have an adequate anchorage capacity. Corrosion protection at the connectors is particularly important to prevent failures. So this corrosion protection at the connectors is particularly important to prevent failures. So before looking into these design aspects, let us look into how these cantilever sheet pile walls can fail. We discussed that this basically two types of failures are possible. One is that soil failure, in other case a material failure or the section failure, which has been provided to has been provided to retain the earth. In this case, failure due to the rotation about point A. In this case, the wall or a section is adequately designed, but it is subjected to a rotation about a point A. That means that the wall is rigid and is undergoing rotation about certain point A from its tip. Now here D is the embedded depth and H is the retaining height, and this is the point of rotation. In such situation, when the wall say deflects away from the surface and this zone becomes active, but when you come to this point of rotation and it is below and this portion of the wall is pushing the wall inside. So here this portion becomes the passive zone, and again in this portion you can see this portion again becomes active zone, because in this portion the wall is going away from this soil. And in this portion here, you have seen that the wall is actually coming and pressing the soil in front of the wall or just below this ridge line. In such situation, and this is called the passive zone, active zone, passive zone and active zone. So when we draw that pressures by using the fundamentals whatever discussed, and here in this case basically Rankine's conditions are assumed to be valid, and like Rankine's coefficients are used for calculating the coefficient of active pressure or coefficient of passive pressure. So here when you draw a net pressure diagram, what we can say is that this is the active pressure which we get, and this portion is the point of rotation which is shown here, and this is the zone where the passive pressure is there, and this is the zone where the active pressure is there, and this is the zone where the passive pressure develops. In case if there is a surcharge, then the additional pressure due to that surcharge will come into the picture with multiplication of Ka factor. So this is the earth pressure diagram for this case which is shown here. So in this case the wall subjected to rotation when actually a soil failure arises and then a rotation is allowed. So this is one of the types of the failure modes of the failure of the cantilever sheet pile wall. Then other failure is that, as I just discussed, is that formation of a plastic hinge at that point. That means that there will not be any failure or rotation about this point. The wall yields about this point and attains the moment which is beyond its plastic moment capacity of that particular section. So this is possible when suppose if there is a possible enhancement in that pressure and the section is not adequately designed, then material failure of the wall can occur and can yield this type of failure. So failure due to formation of a plastic hinge at B, which is shown here. In such situation, here the wall is neither moved towards the soil or away from the soil, it remains intact. So where that no pressure will be there in both the sides, so the zero pressure. and here this portion again is passive pressure, and this portion is again entire zone is active pressure. So this is the earth pressure which is acting at this particular point, and it is actually undergoing moment about this point. That is actually here the maximum bending moment will be concentrated. And for these walls, when we compute the bending moment, the maximum bending moment will occur below its dredge level. So the failure modes of the cantilever sheet pile walls, and we have seen two types of failure. One is due to soil failure where the rotation can occur, the other one is the material failure where the formation of a hinge can occur. Now the previous slides we have seen failure modes of the cantilever sheet pile walls. Now let us assume that we have got anchored bulkheads, and this is the original configuration of the wall, and due to some reason or due to inadequacy of the section, flexure failure of the sheet piling when it occurs, then here that plastic hinge can take place and then can undergo failure. In this case, tie rod and anchor is intact, but the wall section has undergone failure with the deflected surface like this. So this is one of the failure modes for the anchored bulkheads, which is flexural failure of sheet piling. The other types of the failure modes are for anchor bulkheads. They are basically anchor passive failure. So that means that here in this case what happened is that wall is subjected to when it is subjected to these pressures, this particular anchor got pulled out of its position. That is because this side it has got inadequate anchorage capacity, that is passive failures which has occurred, that has resulted anchor passive failure. So there will be excessive movement at this point. In fact, when the anchor bulkhead is there, the moment at this point is 0 and the deflection at this point should be as minimum as possible. Similarly, suppose if there is a chance case where a tie rod which has been kept, which is having inadequate load capacity, in such situation there is a breakage failure or rupture failure of the tie rod can occur. So this is a tie rod failure which is shown here, but here the anchor is actually having adequate resistance, but the tie rod which is actually having very low strength, then tie rod failure can occur and can cause the tie rod failure. Another mode of failure is called whale system failure, where entire system is adequate, but here at this point if there is a bearing plate failure occurs, then we have a possibility of the failure at this point, which is also called as whale system failure. So having seen the failure modes of the cantilever sheet pile walls and anchor sheet pile walls, let us look into how these analysis of these cantilever sheet pile walls, and ultimately we can see how we can do the anchor sheet pile walls analysis. So in this case, analysis of anchored cantilever sheet pile walls is shown. Basically there is a sandy soil both sides on the active side as well as the below the dredge level side. So here entire soil medium is sand, which is shown here. H is the retaining height, and this is the, let us assume that wall is actually rotated about a point O, which is above its tip, and it is located at D naught, which we will try to find out by using the earth pressure diagram, and D is the embedded depth. So as we discussed, the earth pressure diagram will be like this. This is active and this is passive, and this is again due to active case and this is due to passive case. So assumption here is that in the design of this or analysis of this cantilever sheet pile walls is that net passive resistance below point O is represented by a concentrated force R. So net passive resistance below the point O, that is the point of rotation, is represented by a concentrated force R, and that force R actually gives here is assumed to be applied just below this point O, just below this point O. Now let us look in active case, MA is equal to half Ka gamma H plus D naught whole square into H plus D naught by 3. This is obtained, if you look into this slide, this is H plus D naught. So ordinate here is that Ka gamma into H plus D naught. So this is the point, and its CG is acting at this point here. So that is what has been given here. Moment of this active portion here MA is equal to half Ka gamma into H plus D naught whole square into H plus D naught by 3 is the labor arm. Similarly, for passive case, that is in front of the wall, that is here this portion PP into H plus d naught by 3 Pa into this d naught by 3. So MP is equal to half Kp into gamma d naught square into d naught by 3. MP is equal to half Kp into d naught square into d naught by 3. So for equilibrium conditions, Ma is equal to Mp, that moment about that point O has to be 0. So by equating that and simplifying, we can find out, that is equating these two, active case and passive, moment caused by the active pressure, moment caused by the passive pressure. When you equate, you will calculate that you will obtain d naught, which is d naught is equal to h by root over Kp by Ka minus 1. So what we generally do is that once you obtain d naught, then d is calculated by providing some 20% etc. extra. This 20% extra is provided so in such a way that it takes care about the to safeguard against the excessive dredging or scour or presence of the weak pockets in the soil. So d is equal to 1.2 d naught is provided. D naught is obtained based on the deliberations which we have discussed just now. So value of d is increased arbitrarily to safeguard against excessive dredging, scour or presence of weak pockets in the soil. So the value of d is increased by about 20% to safeguard against dredging or scour or presence of weak pockets within the soil. And in the further in the analysis of the cantilever sheet pile walls, it is desirable to evaluate R by equating horizontal forces to 0 and to check the net passive resistance available over the additional 20% embedded depth is equal to or greater than R. So it is desirable to evaluate R by equating horizontal forces to 0 and to check the net passive resistance available over the additional 20% embedded depth is equal to or greater than R. So here it is wrongly shown here, this is PP and this is PA. Calculation of the maximum bending moment can be obtained for Z greater than H. That is, Z is actually started from is 0 at this point and then is measured from this level downwards. So Mz is equal to we can calculate half Ka gamma Z square into Z by 3 minus half Kp gamma into Z minus H whole square, that is this portion, into Z minus H by 3. So for maximum bending moment, differentiate Mz with respect to Z, we will get the location of the Z where that bending moment is maximum, that occurs below its level. So maximum bending moment is calculated for this simple active case for a cantilever sheet pile wall by using this method. The calculation of the maximum bending moment, that is for the Z value greater than H, that is its maximum bending moment is assumed to occur below its dredge level. Then in case of soil which is a clay type, the scenario is entirely different. And we have discussed in the previous class that when the clay is there, the top zone is prone for tension crack, so the tension crack zone can be occurred. Now then we have said that the fundamental equations in earth pressures, like sigma A is equal to Ka gamma H minus 2C root Ka plus Kaq, that is for the active case. Similarly we have got sigma P is equal to Kp gamma H plus 2C root Kp. So let us apply these things. Let us assume that we are having a clay soil or a soil which is having only cohesive in nature, or the soil under undrained conditions where phi is equal to 0. And again similarly in this case, the wall is assumed to rotate about its point toe and this point here, that d is the depth, embedded depth, and h is the retaining height. So the wall is rigid enough and it undergoes a rotation about this particular point. There is also a case where wall can rotate about a certain point, but which is not discussed here. And here in this case, but mostly the rotation about this particular point occurs. So in clay soils, sigma A is equal to Ka sigma V sigma minus 2C root Ka, and sigma P is equal to Kp sigma V plus 2C root Kp. At level of dredge line, that is this point, at point A, sigma A is equal to gamma H minus 2C is equal to at this particular point, that is this pressure ordinate is gamma H minus 2C, this is gamma H minus 2C, and resultant of the passive and active pressure at any depth y below the dredge line, that is we are now trying to come here. If you look into this now, in case if there is a tension crack or the soil is under tension, then this particular negative pressure will occur. Otherwise, if there is a surcharge equivalent to this pressure, then the pressure will start somewhere here, that it will be 0 at this point. So the resultant of the passive and active pressure at any depth y below dredge level is given by sigma p minus sigma a, which is obtained like gamma v, that is gamma h plus 2c minus gamma h plus gamma y minus 2c. And this is the net pressure, and which actually comes to be force C minus gamma h. The force C is equal to, it can be written as 2 Qu, because Qu is unconfined compressive strength of a soil, minus gamma h. So now it actually evolves for the stability of the wall. If you look into it, 2Q by Fs factor of safety should be greater than or equal to gamma h. If this condition is satisfied, then we can say that the wall does not require anchoring or so. If if it is not satisfied, then it requires anchorage at a certain point below the top surface. But if you look into this particular pressure, when we calculate the net pressure, this is the net pressure diagram. So when you look into this is independent of this depth, and it actually have 4 C by minus gamma h which is maintained here and throughout its depth. So when you wanted to calculate the net pressures which are acting or moment about this particular point, then we can actually calculate by taking these forces and then taking moments about this particular point. So in the analysis of cantilever sheet pile walls in clayey soils, we are using the fundamentals what we discuss and applying the relevant earth pressure coefficients. If it is a layered soils, then we need to apply the relevant coefficients, and we can calculate the earth pressures and arrive at the net pressure diagrams, and then calculate the required features and check the required depth whether it is adequate or not. And in this case, for example, this as a thumb rule, for the stability of the wall, 2Q by Fs, if you are able to maintain greater than or equal to gamma h, then actually you can say that the wall is stable. Let us assume that a case where you have got a sandy soil at the top and a clay soil at the bottom, and then wall is rotating about its tip. So at level of the dredge level, that is at this point just below point A. So you look into this, here we have got two types of soil, one is sand, one is clay. So resultant of the passive and active pressure at any depth y below the dredge level is sigma p minus sigma a, again gamma cy, that is gamma cy plus 2c, that is this point, minus gamma sh is that overburden into this, and Ka is now applied below the wall. So Ka is equal to 1 for phi is equal to 0 soil, that is this is the soil which is clay having phi is equal to 0, so K is equal to 1. The factor is not taken because Ka is equal to 1 here, and Ka gamma sh, gamma cy, that is this portion, minus 2c. So when you look into this, when you simplify 4c minus gamma sh, it yields 2Qu minus gamma sh, where gamma s is the unit weight of the sand. To estimate D, take moments about point O. Once we get this, the net pressure diagram is Ka gamma sh, that is due to sand, and 4c minus gamma sh. So to estimate D, take moments about O and increase the obtained D by 40% to again safeguard against excessive dredging or scour or due to any weak pockets in the soil. So this is a case of analysis of cantilever sheet pile walls, and in case if you have a sandy and a clayey soil. Now let us look into the feature like how we can design anchored bulkheads, and we said that these anchor bulkheads are possible when you have got wall heights more than 5 meters or 6 meters also. In such situations, these anchor bulkheads can be provided with a tie rod and a placement of the deadman anchor. So in this in the forthcoming slides, what we look into is that how these anchor bulkheads can be analyzed and how we can calculate the forces in the tie rod, or some it is also in practice to use advanced programs like finite element method, other programs to compute and design these walls. So anchored bulkhead receives its lateral support from penetration into the foundation soil and from an anchoring system near the top of the wall. So, this anchoring system will be at the top of the wall. Sometimes these are called anchored sheet pile walls, and sometimes the anchors also can be at 45 degrees, they are called ground anchors. So, the sheet pile walls are provided either with this type of systems or with ground anchoring system. Stability is due to the passive resistance developed in front of the wall together with the forces in the tie rod. So, when the wall previously a cantilever sheet pile wall without any tie rod here or anchoring system, but in order to manage the deeper excavation, particularly especially in waterfront structures along in the marine environment, to ensure the stability, a passive resistance is developed in front of the wall together with the forces in the tie rods. So, these tie rods have to be placed at certain spacing and then should have a sufficient length so that they will not have interference with the failure surfaces. Basically, these anchored bulkheads are analyzed with two methods and two methods of analysis. One is called free earth method. In this case, a free earth method is used if the depth of the embedment depth is less than 0.2 to 0.3 times the height. H is the height of the retained height, which is actually this height which is shown here. H is the retained height and D is the embedded depth here. Now, free earth method, that is if the D is less than 0.2 to 0.3 times the H, the free earth method is used. In the free earth method, it is assumed that wall is free to rotate about its tip. Wall is free to rotate about its tip. In the fixed earth method, if D is greater than 0.2 H or to 0.3 H, generally the fixed earth method is adopted. That is for this is fixed in such a way that the wall is embedded with a with the deeper depths. So, it ensures the wall fixity. So, fixed earth method is generally used if the depth of the embedment is large, that is more than 0.2 to 0.3 times the H, and the wall is fixed at its tip firmly. So, in the anchored bulkheads, out of this free earth method is frequently used in practice. Here what we note is that this is the wall section and this is that anchor rod or a tie rod force acting away from the wall movement. So, if this is the wall movement direction, this acts in the opposite direction, and this is that active pressure diagram and this is the passive pressure diagram, and this is here the active thrust will occur and here the passive thrust will act. And this is the point A, that is the point where the anchorage has been done with a sheet pile wall section, and H is the retaining height and D is the embedded depth. So, here the depth of the fixity is assumed to be inadequate to produce fixity at the lower end of the wall. So, in this method, in the free earth method, what we is assumed is that the depth of the fixity is assumed to be inadequate to produce fixity at the lower end of the wall. And here in this case, because of the movement, there is a this is the deflection line, this deflection line which is shown here, and here there is no movement and there is a movement towards this side because of this location of the anchor. The wall is pulled inside and there is a movement here. So, the depth of the fixity is assumed to be inadequate. This condition can occur if there is no anchor passive failure and all. So, the depth of the fixity is assumed to be inadequate to produce fixity at the lower end of the wall. And then in case of the fixed earth method, the sheet pile walls are driven to a considerable depth to ensure fixity or a firm fixity to the sheet pile walls. So, here the D is large compared to the previous case, and so that there is no movement at this point, and this is the deflection line. In this case, you can see that the difference in the deflection line, and this is the active pressure diagram and this is the passive pressure diagram, and this is the anchor force which is acting. And here what you have seen is that this is the bending moment diagram which is shown, and this is the point of contraflexure where the bending moment is 0. So, in the fixed earth method, the deflection is shown here like this, and there is no movement of the wall because of the ensuring or a sheet pile, by ensuring that the sheet pile walls are driven to a considerable depth. So, in the free earth method, let us look how we can design, and we are not discussing in detail about the fixed earth method, but the details can be obtained from any soil mechanics textbooks. So, in the free earth method, they assume D, that is the depth of the embedment in front of the wall, and calculate the active and passive earth pressures. So, second step is to calculate active and passive pressures, and if you are having a layered soils, consider, and if you are having say presence of water pressure, that is water and differential water pressure, then differential water pressure has to be considered in the net pressure diagram. So, required depth of the embedment depth D can be calculated or determined from the condition that moment about the anchor point must be 0. That means that you need to take moments at this particular point and ensure that moment is 0. That is, moment of this active thrust about this particular point, moment of this passive thrust about this point is taken and ensure that is calculated and determined depth of D. So, the required depth of the embedment depth D can be calculated from the condition that sigma MA must be 0. This condition yields a cubical equation and which can be solved by substituting trial values. So, this is the case where you have got sandy soil on both sides. So, in this case you have got you will be getting cubical equation, but if this is having a clay, then the pressure diagrams will be same as what we discussed, like 4C minus gamma H net pressure in front of the wall to the entire depth. So, it yields and it can determine the pressure moments about point A, and forces in the tie rod per unit length of the wall. Forces in the tie rod per unit length of the wall can be determined by seeing that the summation of the horizontal forces, that is PA and PP. With that we will be able to calculate the forces in the tie rod. It need to calculate whatever may be the passive forces, whatever may be the active forces, the net difference has to be compensated by this anchor rods or tie rods. So, and also one important thing as we discuss, the location of the anchor plate is very important. So, if this is the wall cross section and if this is the anchor tie rod, and this is, let us say that this is a plate which is located having a depth HA, anchor plate, and DA is the depth of the, that is this tip of this anchor plate from the ground surface, LA is this length of this anchor plate from here, that is length of this location of the anchor plate from the inner face of the wall. Now, when you know this in this case, this particular zone is active zone and this particular zone is passive zone, and this particular zone is again passive zone and this particular zone is active. So, now the location of the anchor plate or LA can be determined like this. This is from the 45 plus 5 by 2 if it is considered, then there is nothing but length of this portion, that is, and this portion. So, this portion which is H plus D tan 45 minus pi by 2 plus dA tan 45 plus 5 by 2. When you put this, then you will get that entire length, that is called LA. So, we have to ensure that it is less than this. Suppose if it is within this point, then there is a possibility that in it will not have any inadequate, it will have an inadequate anchorage capacity. That means that it has to be seen that it is beyond this particular line which is shown here in this case. That is passing through this tip and beyond this line passing through, plane passing through Z. If the HA, that is this point, is greater than dA by 2, the wedge is assumed to develop full height dA. That is, if the HA is greater than dA by 2, then we will assume that the full height is actually participating. But this is the actually common case. If HA is greater than dA by 2, the wedge is assumed to be developed full height. Now, the net pressure on the plate, this particular plate per meter length is given as, this is, we know that passive and this is active. So, this is in case active diagram and this is the passive diagram will come. When you compute and apply a factor of safety and dA is the depth. So, because we assumed that HA is greater than dA by 2, so the entire full wedge is participating. So, half Kp minus Ka into gamma dA square by a factor of safety, which is shown here. So, now the tie rod force per unit length of the wall can be determined by using this expression. Ta is equal to half Kp minus Ka into gamma dA square by factor of safety. That is, L is this length of the anchor per tie rod, length of the anchor plate per tie rod, that is the L. So, by using this, in this particular procedure what we have discussed is that we have to design the value D and increase again by 20% for safeguard against cover and other reasons which we discuss. Then calculate the tie rod force and design the tie rod force and design the section which is required for providing based on the jet, and also see and locate the section safely, so that it will have an adequate anchorage capacity, and also ensure that a good compaction for a fill, so that in this zone, when there is post installation in this particular zone, if adequate compaction of a material is ensured, it is possible that it can have a better anchorage capacity. So in these earth pressure lectures, what we try to understand is how to calculate earth pressures, and based on these earth pressures, we said that how these earth pressures can be used for design of the earth retaining structures. And we discussed about typically two theories. One is Rankine theory, and another one is Coulomb's earth pressure theory, and then we discussed about some example problems in understanding how we can calculate earth pressures for the different conditions.